Hello everyone, today I'll be giving an overview of the Ordovician time period. Within the Paleozoic era, the Ordovician period occurred from 488 to 444 million years ago. The distinction of the Ordovician period was made in 1879 when Charles Lapworth noted that his discovered fossil fauna was different from those found in either the Cambrian or Silurian periods. He named the period after the Celtic tribe Ordovies on whose land he was conducting his research. This period experienced a fairly warm climate and a moist atmosphere. The atmosphere at this time contained about 70% less oxygen than today's atmosphere and about 14 to 16 times the amount of carbon dioxide as there is now. This large amount of carbon dioxide is due to the high sea levels, which covered large continental areas, stopping the weathering of silicate rocks, which is one mechanism through which carbon dioxide is usually removed from the atmosphere. The Ordovician period occurred on Gondwana, the southern of the two great continents at the time. This continent contained what is now southern Europe, Africa, South America, Antarctica, and Australia. Due to seafloor spreading, over this 44 million year span, Gondwana drifted south into the region of the South Pole. During the early Ordovician, sea levels rose by about 180 meters, also due to seafloor spreading, resulting in continental flooding. In fact, the entire North American continent was flooded, which is why marine fossils can be found throughout North America buried under fine sediment. Also, shallow seas formed in the interior of Gondwana, as well as at its edges. While seafloor spreading was pushing Gondwana south, tectonic plate movement created other changes in Earth's geography. The land masses of Baltica and Siberia were pushed into and adhered onto the craton Laurentia, which would create the overall continent of Laurussia by the Devonian period. Furthermore, Gondwana rotated clockwise, causing Rodinia, the landmass on the northwestern side of Gondwana, to collide with the southwestern part of Laurentia. This collision was the first step towards the formation of Pangaea, which would be recognized 200 million years later in the Permian period. Large amounts of volcanism occurred during this period, releasing enormous amounts of ash. For example, the Millbrig Big Bentonite bed in eastern North America is a 1 to 2 meter bed of ash that covers several million square kilometers, or a volume of at least 340 cubic kilometers. It is also possible that an additional 800 cubic kilometers fell into the Yapis Ocean at that time. This ash later weathered into the clay K bentonite. This transformation and other physical and geochemical traits make ash from the Ordovician time period both distinguishable and trackable. Another result of the large amounts of volcanism was that an increased amount of sulfates were introduced into the atmosphere. These sulfates blocked the sun's heat from reaching the Earth's surface, adding to the climate cooling effect that was already occurring as Gondwana approached the South Pole. Volcanoes were not the only geologic structures being formed at this time. Orogenic belts, large mountain ranges, were created as subduction zones and places of converging plates. For example, the Taconic orogeny, a huge mountain range found near Maine, is one of 3 orogenic events that eventually formed the Appalachian Mountains. Here is an example of an Ordovician rock strata found in Tennessee. Ordovician rock strata can be distinguished by thick layers of limestone and other carbonates, as well as by alternating layers of shale and either limestone or sandstone. A ratio of magnesium to calcium in seawater is the determinant as to whether a calcite or a aragonite sea will form. In other words, the ratio determines whether it is a calcite or a aragonite that will precipitate from the seawater. During seafloor spreading, the ratio of magnesium to calcium was reduced beyond the 2 mole threshold ratio, causing calcite to form instead of aragonite. Also, calcium carbonate, deposited by shells and hard parts of organisms that lived in the shallow seas within Gondwana, was another contributor to the widespread calcite content in inorganic matter. Hard grounds, lithified seafloor, as well as ooids, were predominantly calcific. Skeletons of invertebrate fauna were also quite calcific. When the sea levels rose and land mass was covered in water, the intense pressure is compressed to marine debris, sand, and dirt into an especially hard and durable dolomite limestone. This variation of limestone earned a ranking of 4 on the Mohs scale as opposed to limestone's typical 3. This dolomite limestone is denser and less absorbent than typical limestone, as well as being more resistant to the acid found in water in various soils. Formed when the sea levels first rose, as seafloor spreading caused Laurentia and Gondwana to drift apart, the dolomite limestone broke and spread with them, distributing it across continents and making it widely available. As mentioned, Ordovician dolomite limestone is denser and less soluble than regular limestone, making it a great aggregate in asphalt and cement, as well as being useful in road building. Although this form of limestone is denser than normal, oil and natural gases are still mined from these carbonates. Other minerals, such as lead and zinc, can also be mined from these limestones. Other geologic economic advantages from the Ordovician period include the mining of oil shales in Estonia, phosphates in Tennessee used for fertilizer, sandstones in Midwestern United States used in glassmaking, and black cephalopod limestone in Africa used for tabletops and decorative pieces. Next, we move on to the various organisms found during this time period. A notable difference between the Ordovician explosion in diversity and the better-known Cambrian diversification of life is that few new organisms were formed during the Ordovician. Instead, refinements on existing organisms occurred. At about 485 million years ago, the Earth was very hot, with ocean temperatures reaching up to 113 degrees Fahrenheit, which is too hot for most life to develop. However, at the beginning of the Ordovician, the Earth began to cool to temperatures suitable for the great formation of marine life, known as the Ordovician radiation. To start, we have the marine invertebrates. It is important to note that the majority of modern marine phylum formed during this time. The notable marine invertebrates included graptolites, which are a form of plankton, as well as trilobites, brachiopods, mollusks, echinoderms, bryozoans, and conodonts. Conodonts went extinct during the Ordovician Silurian extinction, making them an excellent index fossil. Other marine life includes red and green algae, cephalopods, certain primitive fish, coral, crinoids, and gastropods. To the right is an Arundaspis, a jawless fish. Interestingly, the earliest shark fossils also from the Ordovician period, though only shark-like scales were found, no teeth. And below is a piece of Ordovician coral that was found in Ohio. Intriguingly, 12% of all Phanerozoic marine fauna formed during this period. One of the Ordovician's most notable features is that it marks the formation of land-based fauna, with lycophytes being the first. Also, mosses such as hornworts and liverworts formed, as well as bryophytes, which evolved from the green algae found in the water. The plants of this time, being freshly evolved from marine fauna, had not yet developed internal veins with which to move water. They were non-vascular. This forced them to live in wet environments where they could still get the water they needed externally. Unfortunately, all good things come to an end. The last 3 million of the Ordovician period mark the beginning of an extinction-level event that killed 60% of marine invertebrates and 25% of organism families. There are a couple of theorized causes for this great extinction. The first theorized cause for the Ordovician Silurian extinction is land migration. As noted earlier, during this 44 million year period, Gondwana continued to drift into the region of the South Pole, which was quite unfortunate for the organisms that had adapted to the previously warm climate featured in the Ordovician period. And being out in the middle of the South Pole, surrounded by glaciers, they had nowhere warmer to migrate to. Additionally, when orogenic areas were uplifted, the weathering of the exposed silicate rocks lowered the amounts of carbon dioxide in the atmosphere. This allowed the exceedingly low temperatures to cause large amounts of glaciation, which reduced sea levels by nearly 160 meters. This dried up many of the shallower oceans that had formed on the interior of Gondwana when sea levels initially rose, consequently killing its inhabitants. The second explanation for the Ordovician Silurian extinction, proposed by Brian Thomas and his colleagues at the University of Kansas, suggests that the collapse of a star into a black hole released a burst of gamma radiation directed at Earth. In this case, two things would have happened. Firstly, the radiation would have sufficiently depleted the ozone layer to allow our sun's harmful UV radiation to kill many of the organisms below. Secondly, when the gamma radiation interacted with the oxygen and nitrogen in Earth's atmosphere, nitrous dioxide, the brown gas that is smog, would have formed and blocked out the sun's heat, creating a global cooling effect. Although there is no evidence to suggest that gamma radiation interacted with the Earth at that time, it would help explain why a global cooling effect began during this extinction. This is opposed to the previous theory, land migration, which explains why Gondwana experienced climate cooling, but does not help explain the global cooling effect that began at that time. So to summarize, initially, sea levels rose due to seafloor spreading, creating shallow oceans within Gondwana, allowing spaces for life to develop. Next, over the 44 million year span of the Ordovician, a great diversification of life occurred, comparable to that which took place during the Cambrian. Most notably, the first land-based plant evolved. Thirdly, tectonic plate movement pushed the land masses of the future continent of Laurasia together and also sent Gondwana into the South Pole. Lastly, climate cooling was a great driver in the Ordovician Silurian extinction, which killed about 85% of Ordovician organisms. And although the majority of organisms died, we can still reap benefits from the geologic structures formed during that time. Thank you.